Well, first of all, it is a Big Bang model. In other words, there is a Big Bang, but the Big Bang was not the beginning.
Differences between expected results and actual observations in the Big Bang theory go beyond the acknowledged cosmological challenge. Despite the acceptance of this theory, nearly every prediction linked to the Big Bang faces increasing contradictions from more detailed data. On the other hand, these observations align with the non-expanding universe, questioning the actual happening of a Big Bang. The real issue in cosmology centers on the absence of the explosive Big Bang event, implying that time might lack a clear starting point, or may never have existed. Stephen Hawking's perspective on this issue is summarized in his statement: "The universe has no clear bang. You can rewind to the earliest moments of existence, but asking what happened before would be like asking why you can keep going north when you reach the North Pole." Time, in our usual understanding, loses significance as the universe contracts. It doesn't collapse into a singular point, yet the operational dynamics of physics under such circumstances remain unproven. So what, fundamentally, is time? Does it exist or doesn't exist, as suggested by famous physicist Roger Penrose? Did the Big Bang truly occur? Join us in today's video as we share insights that might entirely reshape your perspectives on the beginning of the universe and the existence of time. In 1981, numerous cosmologists from around the globe gathered at the Pontifical Academy of Sciences, situated within the Vatican Gardens. Stephen Hawking presented what he later deemed his most significant idea, a proposal on how the universe could originate from nothingness. Before Hawking's presentation, all cosmological origin stories, whether scientific or theological, raised the same question: what happened before that? For example, the Big Bang theory, introduced by physicist and Catholic priest Georges Lemaitre, traced the universe's expansion back to a hot, dense bundle of energy. Yet the question lingers: where did the initial energy come from? The Big Bang theory encounters additional challenges, as physicists recognize that an expanding ball of energy would transform into a chaotic mess rather than the smooth universe observed by modern astronomers. In 1980, a year before Hawking's speech, cosmologist Alan Guth recognized that challenges related to the Big Bang could be tackled by introducing an extra element, an initial rapid expansion known as cosmic inflation. This expansion would render the universe extensive, uniform, and flat before gravity could impact it. Inflation swiftly gained prominence as a leading theory for our universe's origin. Nevertheless, the question about the initial conditions remains. What caused the small region, thought to have inflated, into our universe, and what supplied the potential energy for the inflation? Stephen Hawking put forward a solution to the ongoing quest to explore the past. He suggested that there is no absolute beginning or end. During a Vatican conference, the 39-year-old physicist from Cambridge University, still able to speak, addressed the audience, stating, "There must be something truly unique about the universe's boundary conditions, and what could be more unique than the condition that there is no boundary?" The no-boundary proposal, detailed in a 1983 paper by Hawking and his frequent collaborator James Hartle, envisions the universe as a sphere, akin to a sphere with a diameter of 0 at its bottom point, gradually expanding as it ascends. According to the no-boundary principle, the universe smoothly expands from a point of 0 size. Hartle and Hawking developed an equation describing the entire sphere, known as the wave function of the universe, covering the complete past, present, and future simultaneously. This leads to reflections on the origin of creation, the driving force, or any transitions from a time before. In a lecture at the Pontifical Academy in 2016, Stephen Hawking expressed that the question of what existed before the Big Bang was meaningless. As per the no-boundary proposal, there is no concept of time to reference. Hawking likened it to asking what lies south of the South Pole, as both questions are deemed invalid. The Hartle-Hawking state fundamentally changes our understanding of time. Each moment in the universe becomes a cross-section of a sphere. While we observe the universe expanding and progressing from one moment to another, real time involves the relationships between the size of the universe in each cross-section and other properties, especially entropy or disorder. Towards the bottom of the sphere, the correlations become less reliable, and time ceases to exist, replaced by pure space. According to Hartle, a professor at the University of California, Santa Barbara, we don't have birds in the early universe. Later, we have birds. We don't have time in the early universe, but we have time later. Therefore, time inherently lacks a starting point, a version of space-time without boundaries. Hawking suggests a timeless, boundaryless scenario. As you approach the initial timeless state, it transitions to imaginary time. In theoretical physics, the Hartle-Hawking state, named after James Hartle and Stephen Hawking, proposes the universe's state before the Planck era. Hartle and Hawking proposed that if we could go back in time to the universe's origin, we would find that very close to what could be the beginning, time transitions into space. Initially, it only comprises space, devoid of time, as time didn't exist before the Big Bang, making the concept of the universe's origin meaningless. According to the Hartle-Hawking proposal, the universe lacks a conventional origin. It's a singular point in both space and time before the Big Bang. Thus, the Hartle-Hawking state universe has no starting point. Distinct from Hoyle's steady-state universe, it simply lacks an initial boundary in both time and space. The Hartle-Hawking state represents the universe's wave function, a concept used to explore its origins through calculations involving the Feynman path integral. Specifically, it's a theoretical vector within the Hilbert space of quantum gravity theory, describing this wave function. This function depends on the metric tensor defined by the compact D1 dimensional surface, the universe, with D being the space-time dimension. The precise form of the Hartle-Hawking state involves a path integral across all D-dimensional geometries meeting the required boundary conditions on their boundaries. According to the theory, time becomes distinct from the three spatial dimensions familiar today. Further clarification is needed after the universe reaches the Planck age. A universe's wave function, like this one, can be demonstrated to meet the Wheeler-DeWitt equation. Imaginary time serves as a mathematical representation of time in certain approaches to special relativity and quantum mechanics. It proves useful in connecting quantum mechanics with statistical mechanics and in certain cosmological theories. In mathematical terms, imaginary time is real time that has undergone a Wick rotation, where its coordinate is multiplied by the imaginary unit I. It's not imaginary in the sense of being unreal. It challenges the logic of irrational numbers, but is expressed in a form known as IM, or imaginary numbers, by mathematicians. While some may see this as a mathematical concept detached from the real world, empirical philosophy acknowledges that we can only discover mathematical models describing our universe. A mathematical model involving imaginary time predicts not only observed effects, but also effects we can't currently measure. The distinction between real and imaginary exists only in our minds. In the theory of relativity, time is multiplied by I. This can be seen as a characteristic of the space-time relationship, or integrated into time itself as imaginary time, with equations adjusted accordingly. In cosmological physics, imaginary time can be incorporated into specific universe models. Solutions to general relativity equations involving imaginary time aid in addressing singularities where established laws of physics falter. To prevent these points of extreme density and avoid such breakdowns, consider the Big Bang, often seen as a singularity in regular time. However, when represented using imaginary time, this singularity can be eliminated, and the Big Bang behaves like any other point in four-dimensional spacetime. Prior to the Big Bang, there existed only an expansive energy, with no concept of time. Scientific evidence challenging the Big Bang has surfaced, questioning the uncertainties and gaps in this era's theory since the James Webb Space Telescope's launch in 2021. Mounting evidence questions the accuracy of the Big Bang theory, particularly concerning the appearance of light elements like lithium and helium. While the theory suggests a specific amount of these elements formed in the universe's explosion, measurements of lithium abundance in ancient stars within our galaxy contradict the Big Bang's predictions. Stars formed early in our galaxy's history, with a minimal amount of iron and other heavy elements produced by earlier stars. Most of these stars show significantly lower lithium levels than predicted by the Big Bang. Recent data accumulated over the past few years indicates that older stars exhibit reduced lithium content. A study by Lerner, presented at the January 2020 meeting of the American Astronomical Society, suggests that observations of lithium and helium abundance in current old stars deviate significantly from predictions, with the gap widening rapidly. The oldest stars have less than half the amount of helium and less than a tenth of the lithium compared to the Big Bang nucleosynthesis theory predictions. The measured lithium level is less than 1% of the theoretical prediction. Evidence consistently suggests that neither helium nor lithium existed before the first stars in our galaxy. Equally important research proposes an alternative explanation. Stars in the early stages of the galaxy's evolution created these light elements. This explanation, known as the galaxy origin of light elements, or the Golay hypothesis, suggests that the first-generation stars in a galaxy would be of average mass, 4 to 12 times heavier than the Sun. These stars convert hydrogen into helium much faster than our Sun, dispersing helium throughout powerful stellar winds in their final stages. Cosmic rays from these stars, colliding at high energies with other nuclei, generate deuterium and lithium. Despite this data contradicting predictions about the Big Bang, it aligns with theories of galactic evolution that don't involve the Big Bang. Lerner's 1989 paper suggests that cosmic rays from early stars colliding with carbon and oxygen nuclei, along with stars in their giant phase, can explain the creation of lithium. Similar stellar processes, according to Lerner, can also account for the observed abundance of helium, deuterium, and lithium from nuclear reactions in early primitive stars. Recent research, incorporating Golay hypothesis calculations, indicates that early stars not only produce expected amounts of helium, deuterium, and lithium, but also generate other elements like carbon, boron, and beryllium found in the oldest stars. The Golay hypothesis, explained by Lerner, was first detailed in a 1989 paper and has been discussed by others. The predictions from this paper have been confirmed through decades of subsequent observations, providing more accurate predictions than those of the Big Bang hypothesis, based on a broader understanding of star evolution. These conclusions, drawn from observing old stars in our galaxy, find support in recent observations of conditions in newly forming galaxies. These galaxies shine brightly, converting hydrogen into helium at rates much faster than our current galaxy. Research from other scientists published last year indicated that their brightness is influenced by stars with masses around 8 times that of the Sun, aligning with the Golay hypothesis. These structures, too large to form since the hypothesized Big Bang, challenge the traditional timeline proposed by the Big Bang theory. The Big Bang theory suggests that the universe started with a nearly uniform distribution of matter, and structures gradually evolved from stars to galaxies, eventually forming superclusters. However, larger structures have been discovered earlier than anticipated. In 2013, a group led by Roger Klaus found a massive collection of quasars spanning over 3 billion light-years, existing billions of years earlier than expected. This scale surpasses the capabilities of conventional cosmology. Even more extensive galaxy structures were uncovered in 2016 by Hoff and colleagues. Indeed, Lerner noted that given the current slow speeds of galaxies, the vast galaxy cluster structures we observe would need hundreds of billions of years to develop. In a significant study in 1986, Lerner used plasma physics to forecast the universe's fractal structure, encompassing structures with diameters reaching billions of light-years, later confirmed by discoveries. According to Lerner, such structures could only arise in a universe with a history spanning more than 14 billion years. Another factor causing skepticism among scientists is dark matter. The Big Bang theory suggests that the majority of the universe's matter is dark matter, distinct from any matter on Earth. Despite increasingly sensitive experiments on Earth, there's no definitive proof for the dark matter particles predicted by the Big Bang theory. Astronomical evidence, such as the relatively slow speeds of galaxies in the universe, also challenges the existence of dark matter. The significant amount of dark matter predicted by the Big Bang was expected to generate gravitational forces, leading galaxies to rotate at speeds of hundreds of kilometers per second. However, observations indicate an average speed of 50 kilometers per second, challenging the necessity of the large dark matter quantity proposed by the Big Bang theory, as highlighted by a group of scientists. The finely dispersed distribution of dark matter required to avoid high speeds conflicts with the observed clumpiness and uniformity of matter at all scales. Additionally, satellite galaxies around both the Milky Way and the nearby Andromeda Galaxy exhibit disk-shaped configurations, aligning with expectations if gravity originates from ordinary matter. If gravity were linked to dark matter, these satellites would be expected to form in a random sphere. This evidence contradicts the dark matter hypothesis, as demonstrated by many researchers. Crucially, In 2018, scientists emphasized that viscosity effects associated with dark matter would lead to rapid mergers of galaxy groups, making it difficult for many such groups to be observed, a point inconsistent with the observed abundance of these groups. There are simpler alternatives to explain the data without resorting to the Big Bang. Over 30 years ago, scientists demonstrated that electric forces could lead to constant rotation speeds in spiral galaxies, a key piece of evidence for dark matter. These speeds measure the velocity of anisotropic plasma emitted in the galaxy, influenced more by electrical forces than gravitational ones. Some scientists have shown that the outer regions of galaxies, including the Milky Way, the gas moves faster than the stars. This difference can be explained by the influence of magnetic fields on the gas. More recently, scientists provided convincing evidence of the magnetic field's impact on the motion of stars. They found that a significant number of nearby stars are embedded in filaments with lifetimes of hundreds of millions of years. While the authors did not explicitly state this conclusion in their paper, it's evident that gravity alone cannot give rise to enduring filamentary structures. Magnetic fields with observed intensity, however, can influence the dynamics of dense gas filaments. These filaments, in turn, can govern the gravitational motion of stars within them. Magnetic fields, rather than the assumed dark matter, can introduce additional observable forces in galaxies' surface brightness. The hypothesis that the expanding universe is the foundational concept of the Big Bang theory has encountered challenges. Observations of the sizes and brightness of thousands of galaxies contradict predictions based on the expanding universe hypothesis, leading to a significant reevaluation of this fundamental principle. In a paper published by the monthly notices of the Royal Astronomical Society by the lead scientist of LBP fusion, Eric Lerner, titled Observation Inconsistent with Predictions of Galaxy Size and Surface Brightness Growth Based on the Expanding Universe Hypothesis, the study revealed that no predictions regarding the expansion of the universe align with the actual data on the growth of galaxy sizes. All proposed physical mechanisms for galaxy development, including galaxy mergers, face conflicts with observations. However, the paper highlights that the data align more favorably with the alternative hypothesis that the universe is not expanding, and the redshift of light is caused by a different, currently unclear process. This research investigates a significant prediction from the 1930s related to the Big Bang hypothesis, suggesting that objects at very distant distances should appear larger rather than smaller. According to the hypothesis, this phenomenon is attributed to optical illusions caused by galaxies much closer emitting their light. Although this prediction persisted throughout the 1980s, by the 1990s, the Hubble Space Telescope did not confirm it. Instead, Hubble's images indicated that the farthest galaxies appeared smaller in reality. As a response to this discrepancy, a group of researchers proposed an additional hypothesis, suggesting that galaxies indeed grow in size over time. Therefore, very distant galaxies, when observed from billions of years ago, were theoretically much smaller than galaxies that appear today. In the 1990s, the intrinsic sizes of galaxies, as indicated by the evolving galaxy theory, decisively contradicted the optical illusion predictions from the 1930s. Lerner's paper subjected the quantified predictions from developing galaxy theories to scrutiny by comparing them with observed sizes of thousands of spiral and elliptical galaxies, utilizing HST observations from 2004 to 2014. The paper focused on galaxies with similar near-ultraviolet brightness. The observed data did not closely align with predictions suggesting that galaxy sizes increase proportionally to the rate of universe expansion. The process hypothesized for the development of elliptical galaxies, involving merging with other galaxies, occurs at a rate almost 10 times slower than the growth rate proposed in the hypothesis. An even more significant discrepancy emerges when comparing the gravitational mass of distant galaxies, calculated from their rotation speed and size, with the mass of the stars within them, calculated from their emitted light. Predictions based on the expanding universe theory yield a gravitational mass smaller than the mass of the stars, a scenario inherently impossible. Contrary to this, Lerner observes that predictions rooted in a non-expanding universe offer a more accurate fit for both spiral and elliptical galaxies at all distances, with an accuracy of a few percent, regardless of the distance. In a non-expanding universe, galaxies with a certain brightness exhibit the same size, aligning with the predictions of a non-expanding universe hypothesis. According to Lerner, In this hypothesis, the straightforward linear relationship between the redshift of light and distance arises from something affecting light during its travel, not the expansion of space. While the cause of this phenomenon remains unknown, the linear relationship and the concept of non-expanding space generate predictions that align with the observed data, unlike predictions associated with an expanding universe. The Big Bang Theory faces several issues that supporters dismiss as anomalies. However, these issues fundamentally contradict all predictions of the theory. In an attempt to address challenges, proponents of the theory continue to introduce additional parameters to accommodate new data that deviates from predictions. This has led to the adjustment of over 20 parameters, and notably, the theory struggles to make accurate predictions of new results, an essential characteristic of a robust scientific theory. Recent findings from the BICEP-3 instrument compelled researchers to incorporate even more parameters into the theory to reconcile discrepancies between BICEP-3 and Planck results. In contrast, hypotheses aligning with a universe devoid of a temporal beginning and without a Big Bang can offer a simpler explanation for the data contradicting the Big Bang theory. Alternative hypotheses suggesting a universe without a beginning in time and lacking a Big Bang offer a simpler and more cohesive framework to make sense of conflicting data. Unlike the ongoing adjustments and additions of parameters in the Big Bang theory, these alternative perspectives maintain a straightforwardness that aligns with solid scientific principles. The flexibility of the Big Bang theory, shown by the continuous introduction of parameters to accommodate new data, raises concerns about its foundational strength. Scientific theories usually prove their robustness by predicting new outcomes, a criterion where the Big Bang theory faces challenges. On the other hand, theories suggesting a universe without a specific beginning, challenging the idea of a Big Bang, offer straightforward explanations. In ongoing scientific discussions, it's essential to seek theories that can explain observations without requiring numerous adjustments, contributing to a better grasp of the cosmos. As the scientific community deals with these challenges and considers other explanations, the search for a complete cosmological model continues. The Big Bang theory, relying on more than 20 adjusted parameters, prompts a reassessment of its fundamental assumptions. Facing discrepancies between BICEP-3 and Planck results, the growing complexity added to the Big Bang theory emphasizes a possible requirement for a more straightforward paradigm. The simplicity suggested by hypotheses proposing a universe without a time-based beginning and without a Big Bang provides an intellectually attractive path for further exploration. The persistent quest for a consistent cosmological framework that precisely mirrors our observational data and aligns with scientific inquiry principles highlights the ever-changing nature of astrophysical research. As the scientific community continues exploring these frontiers, the progression of our comprehension of the cosmos remains an exciting and continually evolving journey. In the exploration of the cosmos, being open to reconsidering established theories and embracing alternative perspectives is crucial. The changing landscape of cosmological inquiry requires finding a balance between adapting existing models and considering new concepts that align better with observational data. The challenges in accommodating diverse observations are evident in the accumulation of parameters in the Big Bang theory. On the other hand, hypotheses suggesting a universe without a temporal origin and free from a Big Bang aim for a more straightforward and unified explanation. In the pursuit of scientific understanding, it's vital to critically assess theories, recognizing both their strengths and limitations. The interaction between competing ideas and the ongoing refinement of our cosmic narratives push humanity toward a deeper understanding of the vast mysteries unfolding in the cosmic tapestry. As researchers navigate the complexities of the cosmos, exploring alternative hypotheses becomes a crucial catalyst for intellectual growth and the advancement of our collective knowledge. We would love to hear your thoughts on this. And if you found this video interesting and enjoyed watching it, please give it a thumbs up and stay tuned for more content.